maybe we will continue discussing a paper and or do you want me to start industrial chem?
Industrial chem.
Or industrial chem? Or continue the discussion?
Vote.
No, let's have the lesson.
Okay, let's
No fighting.
Please, we need to get up the schedule.
The mixation
Okay, we'll start industrial chem then. Have you brought the worksheet from before? No, then don't worry, I will be writing on the worksheet and I'll send you a copy. So, and do you mind letting like Janet in? Oh, okay.
She needs something to like, I see something wrong with it. Oh no, what did you do? 21-year-old, so scared. She almost asked me to say that. I'll take you out after you're 18 years old. I'm 21, I'm still here. But she's still like, how
Okay.
I will take you out. If you're not going to university, out. Out of my
So,
home.
just a moment, let me pull up the,
I thought your family was
right.
no.
Okay, everyone, do you have the worksheet from before on the industrial chem? I think I sent it out earlier, like hard copy, remember? If you don't have it, I will write on this copy and I'll send you all this.
Yeah, you just like write, no.
Okay, right. So, what do we actually study in industrial chem? Okay, like it's a bunch of things that we can do to speed up reactions, okay, and boost the yield, okay, on products. So, and of course, the word industrial chemistry is more about industrial processes. Okay, so the first thing we look at is, and maybe, I'll wait till, that is, something I'll just put it on the side. So we have industrial chem. So in industrial chemistry, we look at, make sure you also check the answers to the paper. Okay, and if you need a blank paper to work on, don't look at the answers here. Okay, you can come to me later.
This was new chapter, right?
Yeah, this is the first elective, okay? So right, industrial chem. So we will look at industrial processes. So in industrial processes, we want to turn the so-called raw material into bulk material, or bulk substances, okay? And finally, we turn them into synthetic products. So synthetic meaning man-made, of course. So, and most of the raw material, they are natural. Okay, at least they are naturally found. Okay, but the products, okay, most of the time they are synthetic. So an example of, right, okay, be quiet, okay, right. So we have this so-called industrial process here. Okay, it's the conversion of raw material through bulk material into synthetic product. An example would be, petroleum. So petroleum, not to be confused with petrol, is crude oil. So it is a mixture of many hydrocarbons. Okay, so remember hydrocarbons like alkanes. Okay, those are hydrocarbons. When you do fractional distillation, okay, on petroleum, you can maybe collect some lighter fractions, okay, like naphtha. So naphtha is one of the many fractions you can get from petroleum in bulk. So bulk material means you make many hundreds of thousands of tons of every day around the world. So bulk material. From naphtha, we can then make things like medicine, like plastic, or maybe detergent even. Remember there's soapy and soapless detergent, right? Which of those detergent is made from, crude oil origin? Soapy. Well, actually soapless. Okay, soapy detergent, they come from fats, right? Remember? Yeah, so you may want to add the word soapless here. Okay, so soapless detergent. Soapy detergent are made from fat, but we are looking at the detergent made from petroleum now. Okay, so this must be soapless detergent. So these are things we can make. Okay, our these raw materials. And in all industrial processes, we will need to look at how we can increase the yield. So you can put down in industrial processes, okay, we want to increase both the rate and the yield. And we already learned factors that will affect the rate and yield of reaction. So, and yield, remember rate is how fast the products are formed. And yield is how much products are formed. So they are affected by different factors, okay? Rate is affected by which 5 factors?
Concentration,
Concentration,
temperature,
pressure,
catalyst,
the addition of catalyst, and
pressure.
yeah, changing surface area, okay? So you have catalyst and surface area. But you may want to make this a table. Just put down tick here. Rate is affected by these 5 factors. But yield is only affected by how many of the same factors? 3. The first 3, okay? And for pressure, I'm putting tick or cross here. Why? Do you remember what kind of reactions were no change in yield when I increase or decrease the pressure? Is it when the number of gases on the 2 sides are equal, or when the number of gases on the 2 sides are different? When the number of gases on the 2 sides are equal, there will be no change in yield, remember? And this is why I put tick or cross here. Depending on, yeah, if you don't know what this is, you might want to refer back to the equilibrium chapter. So if you have 2 reactions here, N2 plus 3H2 gives NH3. Compared to, for some reason Janet hasn't joined the student, maybe you want to give her a nudge, okay? Thank you. Okay, so, and then there's HI. So take a look at the number, 1, 3, and 2. 1, 1, and 2. For the first equilibrium, there are 4 gases on the left and 2 gases on the right. But for the second equilibrium, both sides have 2 gases. That means, in which reaction would increasing pressure increase the yield? The first or the second equilibrium? The first one. So can you put down increasing pressure would help nudge the reaction to the right, shift the equilibrium to the fewer molecule side. So increasing pressure can boost the yield for this equilibrium. But for the second equation, unfortunately, you see that there's the same number of gases on the 2 sides. So you can put down for the first equilibrium, increasing pressure can increase the yield of ammonia for our first reaction, but not so much for the second one. Okay, so you can write down increasing pressure has no effect on HI yield. This is why I put both a tick and a cross here, as the answer is it depends. Depends on the number of gases on the 2 sides. So just a warm reminder on this part. Okay, we have discussed this in the equilibrium. You can refer back to the notes.
Second is zoom in.
Yes. So pressure, increasing pressure can increase the yield of ammonia, which is why I put a tick here. But then I also put a cross here, and I wrote an or in between, because what about this equilibrium then? This equilibrium with same number of gases on the 2 sides. In this case, increasing pressure has no effect.
So you can add the chasing constant.
You mean on a check right now? Okay. So then I will just pause the video. Okay. Later. Right now, let's continue. Okay. So what else do we need to look at in industrial processes here? You see, we want to collect the desired product. Okay. And then so you can put down what these are. So we have reactant, or you can say the raw material. They will be turned into products and the so-called side product or byproduct. Okay, so side product or byproduct. So when I say product here, I mean the desired product. Okay, usually only one of the products is what you really want from the reaction. All the other stuff that is formed alongside the desired product, they will be called desired products or byproducts. They are considered as some kind of a waste. Okay, so this is waste. Yeah. And in the process of converting reactant into product, you may want to add water. So water is a very important coolant. Okay. So water is an important coolant. So act usually as a coolant. Okay, so this is why we need water. And for some reactions, water is a raw material, like hydrolysis. Okay, so hydrolysis reaction requires water as a reactant. But most of the time, water will just act as a coolant. So this is what we do in industrial chem. We try to optimize the process here to make more of the desired product and make less of the side product. And do you remember from our discussion last time, if there are two pathways leading from the reactant to the same product, and one has more steps, the other has fewer steps, which of these pathways is preferred? Is it the one with more steps or the one with fewer steps? Fewer steps. Because the more steps there are, the lower the yield. Because every time there will be a discount, right? Remember, so if you have something that looks like this. Let's say ideally, there's a one-step reaction that will go from a reactant to product. And then alternatively, there's another reaction that will convert the same reactant into the same product, but at a cost this time. Okay, there are 3 steps. Okay, so there are 3 steps. And assuming that each step has a yield of 90%, now remember that discount analogy. If you get a 10% discount just once, well, there will be, it will cost a certain amount of money. But if you do 10% discount 3 times, this will cost less. Okay, and therefore result in less product, and here there will be more. So this is another thing we look at in industrial chem. Okay, we want to optimize the reaction. And okay, next up, here are just some examples of things you need to know. Why do we want to make a lot of synthetic products? Because different synthetic products have different uses in different fields. Okay, like the medical field, like aspirin. What is one property of aspirin? You remember? Painkiller, okay, and then there's antipyretic, okay, fight fever, and it thinns blood, okay, so they will ask you about those properties. And it must not be taken with which chemical? Alcohol, or else there will be stomach bleeding, okay. So penicillin, those of you who take biology will know, is an antibiotic, not antibody, but antibiotic, okay. So and then the other stuff, just remember it. I think this will only appear in MC, where they ask you, which of the following some examples of synthetic products. Okay, if you see petroleum here, petroleum is just a raw material, it's not a synthetic product. Okay, so no what to put in here. And then what is more interesting is the synthesis of vitamin C. Okay, if we don't have enough vitamin C in our diet, okay, we will have scurvy, okay, we'll have bleeding gums, okay. So we now look at the synthesis of vitamin C. Right, so the official name or the chemical name of vitamin C is ascorbic acid. So ascorbic acid, okay? And it will give you this, pathway, okay, in the exam. And they ask you to identify what the reaction is, okay, in each of the steps here. So let me just copy this out and I'll ask you something about the, like a reaction that has happened here. So can you tell me by comparing the first, okay, by the way, what do you call the stuff that you add into a reaction? You call these the reactant, right? So this is the reactant or the raw material. And this, we call it the product. What do you call everything in between? Intermediate, right? Yeah, so very good, you remember this term. So you have reaction in its quest to become a product. It will have to go through these so-called intermediates. So intermediates, okay, if you don't quite remember what it is, they are something formed in the middle of the reaction, but then they will be consumed again in a later step, okay, to form our final product. But can you tell me what is the type of reaction that happens at A, B, C, and D? So let me put down the question here first. Identify the type of reaction, okay, at like A, B, C, and D. Well, by type, we know a lot of reactions already. It can be neutralization, It can be combustion, it can be decomposition or displacement or oxidation or reduction. So that's what we mean by type of chemical reaction. Write this down. So when they ask you, oh, what are some types of chemical reaction that you have learned? Well, you learned a lot already actually. Write them all down. Substitution. Okay, I want you all to think of one example of each. Okay, I don't want a lot, but I just want one example from all of you, just to check if you remember stuff from organic chem. So substitution. I want one example of addition. I want one example of elimination and neutralization, which is not from organic chem, and decomposition. And sorry, what was it? Oh, what's elimination? Elimination of water, elimination of, do you remember concentrated sulfuric acid? It can dehydrate, okay, alcohol. So elimination of water would be dehydration, okay? Right, and then there's one more. Actually, two more, sorry. Okay, oxidation and reduction. Oh. Okay, right, yeah, so we have oxidation and reduction. Can you give me one example of each? I accept any answer here as long as it is a substitution reaction. Do you remember there's one pathway that we go like, that we use a lot in organic chem, the convert between two substances? Alcohol and, no, it's alcohol and haloalkane. If we want to substitute the OH group in alcohol with a halogen, what do we use? I still remember that page. I drew something that looks like a yes, PX3 or BCl3. Let me show you where that page is here. Do you remember this roundabout?
Yeah.
You go on and on, okay? Alcohol, when you convert it into a haloalkane, you use PX3. I said X because this can be any other halogen, like the or I. So if we want to go from this to this, we use PX3. But back from haloalkane to alcohol, we use aqueous, okay, sodium hydroxide. So this is what we can put in here. So substitution, you can write ROH plus PX3 gives RX plus, what is the other product? What is the other product that you get when you halogenate alcohol?
Water.
No, but it's phosphorus acid. Right? Okay, so remember, time to do revision. Okay, and then we have addition. One example of addition. Can I have one example of addition? Remember platinum? When you put platinum, when you use platinum as a catalyst and you add hydrogen to an alkene, alkene plus hydrogen produces alkane with an A. Yeah, do you remember, where is it? Oh, here. Oh, okay. Platinum as a catalyst. When you add hydrogen to alkene, you get alkane. So this is an addition reaction. There are many other addition reactions as well because alkene can react with, where was it? I think I put down the alkenes somewhere here. Like, yeah, alkene can react with a number of stuff. Oh, here. H2, HX. X2, okay, yeah, these are all addition reaction because two things react to form one thing. That's what addition means. Okay, when you add hydrogen, which is one reactant, to alkene, the other reactant, there's only one product formed. Whenever you get only one product, after you mix several reactants together, those reactions are called addition because you only add things. You did not take away anything out, right? So addition, this is. So just one example. So we can put C2H4 plus H2 in the presence of platinum, form C2H6. What is the name of C2H6?
Methane.
How many carbon?
Ethane.
Ethane, yeah, ethane. Okay, and then there's the elimination of water. Do you remember what the dehydrating agent is? It's concentrated sulfuric acid. Alternatively, we can use aluminum oxide. Okay, can you predict the product? We discussed this some time ago. Okay, when you dehydrate.
Alkene.
Yeah, what is that alkene? When you dehydrate specifically ethanol. Ethene, yes, because that's what dehydration means. You take these out and you turn this CC single bond into a double bond. So this is what results. So you have C2H4. Okay, so you have C2H4 and don't forget to put H2O in here. Okay, if you don't put H2O, it will not be balanced. So that's what dehydration means. When you dehydrate substances, you remove OH from one carbon, you remove H from an adjacent carbon. Remember this?
Yep.
Okay, and then neutralization, something a lot easier. Okay, not about organic chem anymore for these reactions. Anyone can give me an example of neutralization reaction?
Sodium hydroxide.
What is the simplest acid and base you can think of? Yeah,
HCl.
maybe HCl and NaOH forms NaCl and H2O. What about decomposition? Let's go back to the lime cycle thing. Yeah, limestone, when you heat it, what will it turn into? CaON,
Water. CO2.
CO2. They cannot be water as they are all hydrogen in calcium carbonate. Okay? And for combustion, it's easy. I give you the example. Methane, when it reacts with oxygen, it will form CO2 and H2O. And oxidation, reduction. Can you give me a reducing agent that will undergo oxidation? An example. What are some examples of reducing agents? You learn in redox. Iodide, for example, will be oxidized into I2, okay? And let me remind you once again, on the mock paper, I see a lot of students confusing halide and halogen. There was this one question that asks you what happens when zinc reacts with iodine, and I see a lot of answers. Yeah, it really opened my eyes to it because there can be 5 different answers for one single question. Okay, so be careful. Let's not make this mistake anymore. When you see iodine, it must be something 2, okay, or chlorine or fluorine. Something ending in ine must be diatomic molecule, I2. And so the products will be Cn2 plus N2I minus. Can you identify the oxidizing and the reducing agents here? First,
Second.
what
Give us.
undergo oxidation?
Zinc.
Zinc. Okay, finally, none of you said zinc 2 plus. Okay, excellent. Because last lesson, some of you said zinc 2 plus is oxidized. No, only the reactions can be oxidized, right? So what is reduced?
Iodine.
Iodine, okay, is reduced. So this guy right here, write down the name, is iodide. Whenever you see something ending in suffix ine, it must be X2. Whenever you see something, well, not whenever, but when you see a halogen ending in IDE, it must be X minus. Okay, don't confuse these two, they are very different. Okay, so which substance is the oxidizing agent? Iodine, yes, I2 is the oxidizing agent because it is reduced. Okay, because it is reduced. The oxidizing agent is the one that is reduced. And then, which substance is the reducing agent?
Zinc.
Zinc, yes, zinc is the reducing agent. Is this clear?
Yep.
Reducing agent is what is oxidized. Okay, yeah, I know what I'm saying. It's the opposite. Reducing agent is what is oxidized. Okay? So therefore, if I ask you for an example of reduction, that means we're looking for what kind of agent?
Zinc.
Oxidizing agent.
Oxidizing.
What are the 2 oxidizing agents that you all should be very familiar with in organic chem? K, MnO4. What would MnO4 minus be reduced to? Mn2 plus. Okay, so what is the color?
Purple to colorless.
Purple to colorless. Okay, purple to colorless. And what about the other oxidizing agent?
Dichromic.
The dichromic. It will be reduced to
CR.
what is the color change?
Orange to orange.
Orange to green. Okay, yeah, orange to green. Purple to colorless. Orange to green. Okay, so these are reduction. So now, you can finish copying these words here. You need to know all these reactions. You learn it in different parts, scattered all over, all around, like the DSE chemistry. So, and now if I give you these 4, 1, 2, 3, 4, 5, 5 chemicals, can you tell me what kind of reaction must have happened between the first and the second chemical here? Can you tell me what is changed?
There's no from ketone to
Oh, is this an ester? Is this a ketone? This is not one of these two.
aldehyde.
Aldehyde. Okay, can you
Con.
circle all the functional group present in glucose? Yes, there are many hydroxyl group. Okay, so you can circle them. Hydroxyl, 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 hydroxyl. So these are hydroxyl functional group, which indicates that it is an alcohol. What else? There's one more thing. Aldehyde. Yeah, this is not an ester, and this is not a ketone. Okay, because ester has a COO group, and a ketone has just a CO double bond without an H on the side. So this is an aldehyde. So what happened? As you undergo reaction A, you see the aldehyde group is converted to a hydroxyl again. So what must have happened? Is it oxidation or is it reduction?
Oxidation.
Oh, remember the MTR pathway here. Primary alcohol can be oxidized first into
A reduction.
aldehyde first. And I think your answer is to go from aldehyde back to alcohol, that must be reduction, right? So can you draw this pathway if you have forgotten about this? So going forward, we call this oxidation. It is done by oxidizing agent. Okay, so K2Cl2O7/H+. Okay, I see in the answer some students did not put down acidified K2Cl2O7. They only wrote K2Cl2O7, which is not good enough. Okay, it has to be acidified. So this is oxidation. And going backward, it's reduction. Oh, and for this one, I also saw a few of you mix up LiAH4 and NABH4 and you create some kind of a chimera, like NaLiAH4 or something. Okay, no, it's either NaBH4 or LiALH4. So which of these can be used with water?
NABH4.
NaBH4. Okay. What about LiAH4? What must it be used with? Dry ether, because it will explode in water. Okay, so you can use aqueous for NaBH4, and you must use dry ether with LiAH4, but they help you go backward. Yeah, that's why I compare it to a train station. You can go forward or you can move backward, okay, depending on where you want to go. So what is this reaction then? A, is it oxidation or reduction?
Reduction.
Reduction, okay, so write down A is reduction. Because the aldehyde group is turned back into which class of alcohol? Primary, yeah, primary alcohol. So what about B? Let's do a compare and contrast here, okay, when you look at the functional group, what is changed? There's only one change.
From alcohol to alkene.
If it is an alkene,
Aldehyde to alcohol.
no.
No.
Can you see this group turning from?
Elimination?
What is this? This is aldehyde, right?
Yeah.
What is this? Ketone. Yes. Do you see the difference between aldehyde and ketone? Aldehyde has C on one side, H on the other side of the CO double bond. A ketone has C on both sides. So I understand the frustration. Okay, if you constantly mix up aldehyde and ketone, this is the only way to not make mistake. Is to look at what is next to the CO double bond. If you see one H and one C next to the CO double bond, this is not ketone, this is aldehyde. And this is ketone because it's surrounded by two carbons. Don't mix them up, aldehyde and ketone. So this is a ketone. If aldehyde comes from primary alcohol oxidation, okay, what does a ketone come from? The oxidation
Oxidation.
of which type of alcohol? Secondary, okay, so, and you can see that this alcohol is actually a secondary alcohol, you see. Focus on just this OH group. Focus on just this OH group. You trace it back to this carbon. How many other carbon is this carbon bond to? Two. So therefore write down this is a secondary alcohol. Makes sense, okay? And what about this? You know an aldehyde comes from primary alcohol, right?
Yeah.
Let's confirm this. Okay, look at the OH. You trace it back to this carbon. How many other carbon is this carbon bonded to? One. So primary it is. Okay?
Yeah.
So you need to not get distracted by the other OH group. Okay? So write down B is oxidation because we went from a secondary alcohol to the ketone, RCOR prime. What about the third reaction, C? What has changed? There's something new.
To alcohol to acid.
Yeah, alcohol to carboxylic acid. Okay, so circle this group. So we have, so which class of alcohol can be terminally oxidized to carboxylic acid? Yeah, first degree or primary. Okay, so C would again be oxidation. But this time we are turning a primary alcohol all the way to a carboxylic acid. So what is the condition for turning a primary alcohol straight into carboxylic acid? Do we do distillation or reflux? Reflux. Okay. Yeah, and I'm happy that many of you answered that question right in the mock paper. Okay. Why you shouldn't do reflux? Okay, in that question, because if you do reflux, you don't get aldehyde. You'll get carboxylic acid. Okay. So I'm pleased with the answer in that question. So finally, D is the hardest. So let's do some counting. I want to just see if all of you can count properly, okay? Can you count the number of carbon? I want you to tell me the molecular formula of this guy. Yeah, no need to copy it, but you can just count, just looking at this formula on the screen. So molecular formula. Show me how many C, how many H, how many O there are. Okay, don't yell out the answer. We'll check the answer in 30 seconds. You can count quietly first. For this one, I will write it for you. I don't think anyone would count this incorrectly because every C and every atom is shown to you, but not here. Some of the atoms, they are omitted, okay? And you have to count them. So let me just put down how many CH and over here. I'll give you some time to check this out. So you have 1, 2, 3, 4, 5, 6, so C6. H10.
10.
1, 2, 3, 4, 5, 6, 7, 8. Yeah, there are 10 hydrogen here. Okay, what about this one?
C.
How many C?
6.
C6.
H.
H8.
6.
1, 2, 3, 4, 5, 6. Okay, so D is the hardest. What do you think reaction D is? If it went from C6H10O7 to C6H8O6.
H2O is what? Elimination.
Yes, both of you are correct. Elimination or dehydration. Let's just do some math here. C6H10O7 minus C6H8O6. What is removed?
Water.
H2O. Can you all see that H2O is removed? Yeah, equals H2O. So that means this is elimination or dehydration.
Oh, that's what it is.
Right, yeah, this is the hardest. So put a star here. I put a star here for a reason. Okay, so elimination of H2O. So if you're asked to suggest a possible substance that can carry out this step, that would be what can carry out dehydration?
Concentrated sulfur.
Or
Aluminum.
aluminum oxide, yes. Okay, so you see this kind of concept, okay, you won't just see it in the core, but also in the elective, okay. So this is the hardest. And this resultant product is ascorbic acid. Okay, so it's ascorbic acid. So next up, you just have to know that there are two different pathways to mix vitamin C. You see A, B, C, D, they are real steps that happens in an industrial plant. Okay, this is actually how we make ascorbic acid. It's not because I want to turn into question that I give you so many steps in between, but this is actually how we go from glucose to ascorbic acid in real life. And there are two ways to make vitamin C. Okay, so the first way is known as the Rich-Stein method. Okay, so second is called two-stage fermentation process. So two-stage fermentation process. So what these two terms mean is that for Richstein process, okay, so it uses a combination of chemical, okay, reaction plus fermentation reaction. So for those of you who do biology, you know fermentation. We use a lot of microorganisms, okay, in the manufacture of wine, in beer. We can also use the help of bacteria for some of these reactions. So some of these reactions, they can be carried out not by chemicals, but by bacterial, okay, fermentation. So you have bacterial fermentation, okay, or yeast fermentation. So you have yeast or bacterial fermentation. So some of these steps, A, B, C, D on top, they of course can be done by chemical, like dehydration can be done by corn sulfuric acid. But using chemicals is expensive, okay, and that may be hazardous, some of the chemicals. So we will use yeast or bacteria to help in some cases. While two-stage fermentation, it is basically the same thing as Richstein process. Okay, so basically the same thing as Richstein. Yeah, but one chemical step is replaced by replaced by fermentation. So there is more involvement of bacteria and yeast in two-stage fermentation than in Richstein process. Okay, but the reactions are the same. You're turning the same substance through the same intermediate into the same product. You still have D-glucose, D-sorbitol, L-sorbitol. You don't need to know these names. You don't have to memorize these names. So you have the same reactant and products and intermediates involved in these two stages, in these two processes. It's just that Richstein used less, yeast and bacterial fermentation. There's more chemical reaction. So if I really have to put a number here, you can say Richstein uses maybe 80% of this and 20% of this. Two-stage fermentation uses more, okay, yeast and bacteria. For that, maybe it's close to 60% and 40%. And this is to give you an idea. But the same reactant, intermediate, and products are involved. Okay? Yeah, and the name is not so important. Okay, like to me, it's just the reaction that's more important. You need to know what they are. Okay? They will give you these structures. Nobody will need to memorize the structure in here, but make sure you can identify them properly. Okay? Right. So that's the only interesting thing about industrial chem, and then the rest are boring stuff. Okay. So we look at the first boring part of industrial chem. Rate equation. So you all should remember that rate is affected by concentration, like we saw. But sometimes increasing concentration will increase rate linearly, while at other times changing concentration will increase the rate exponentially. So in order to describe how the concentration affects rate, we have to use something called rate equation. So this is also on the worksheet, but you may want to put this on the note as well. So rate equation. So recall that, okay, in a reaction, so consider the reaction below. When you have A reacting to form B. To keep things simple, I'll just put one reactant and one product in this reaction here. Can you show me a trace of the concentration time graph for A? How does concentration of A change over time? It will decrease until it falls to 0, because this is the only reactant. Okay, and I'm also happy that in the pre-mock, when they ask you this question, showing you the color, and that did not fall to 0, and they ask you what can you conclude from that. Many of you, okay, answer that I2 must be so you see iodine is the brown substance here, right? So if the brown color did not fall to 0, it means iodine must be in excess. So many of you come to this correct conclusion. I'm happy, okay? And in here, we need to build on that, okay? So when you plot the concentration time graph of A, so a plot of concentration of A against time, so this is what it looks like. Okay, so you have concentration of A against time. So it should fall, and this time it should fall straight to 0 because this is the only reactant. If there were other reactants, okay, and that this is the excess reactant, it will just plateau. It will not fall straight to 0. Okay, yeah, just remember that. And can you describe how the rate change over time? When is the rate the highest? Initial rate. Okay, yeah, and for the initial rate, you need to know how to find it. It's to find the slope of the tangent drawn at t equals 0.
I lost.
Yeah, okay, yeah, that's where some of the students, quite a few of the students are lost the math. Okay, so remember that. You draw a tangent here. So this is the slope of the tangent at t equals 0 second, and then you repeat this process. You can see that the rate decreases over time, okay? So recall that rate decreases over time. And you know what's the most interesting thing? It is that when you try to find the rate at a particular concentration and you plot the graph again. So here you have rate and concentration of A. If you collect these values again, you will get another graph here. Okay, so let's say this value here is, I don't know, like maybe 0.8. Let's say the rate is the fastest at the beginning. Let's say it's 10. So you have 10, and this is 0.8. For the second point in here, let's say the concentration drops to 0.6. The rate falls to, I don't know, like maybe 8. Yeah, you see another kind of relationship here. If you find the rate at a particular concentration, and you plot this graph again, you will get another plot. Okay, so this is the plot of rate against concentration. Okay, so plot of rate against concentration. Concentration of A. You will see this. Right, so you will see a straight line. Okay, so something like this. So this is what you get when you plot rate against concentration. And from here, we can write something called the rate equation. Okay, so don't confuse these two graphs in here. The graph on the left, we call it the concentration time graph because you are plotting concentration of its reactant against time. The graph on the right, we call it the rate concentration graph. Okay, that means what is plotted as the y and the x-axis respectively. For concentration time graph, concentration is y, time is the x-axis. For rate concentration graph, rate is the y-axis and concentration is the x-axis. For different reactions, the rate concentration graph will look different. Okay, we have 3 types of order of reaction here. But first, let me put down what a rate equation is. So a rate equation, so for a reaction with a single reactant A, the rate equation will be rate equals K times the concentration of A. And this is a lowercase k. Not to be confused with the other k you learn in the equilibrium chapter. What is the name of that k you learn in the equilibrium chapter? Equilibrium constant. Okay, so k in lowercase, we call it rate constant. You saw another k in another chapter, which is a completely different concept. It's Kc. That's the equilibrium constant. Well, from the name, you know you learn it in 2 different chapters. Rate constant, you learn it in here, in rate. Equilibrium constant, you learn it in the equilibrium, but they're not the same. Okay, so they are not the same. So therefore, be very careful when you write this equation. And then we are not done with the equation. The equation will have the concentration of the reactant raised to a power. Okay, so let's look at what this means. The whole thing, we call it the rate equation. So the rate equation is the entire thing in here. And K is what we call the rate constant. And concentration of A, so this is the concentration of the reactant. And then we have finally M. M is what we call the order of reaction. Yeah, a very interesting term. Okay, order of reaction. So, what does this equation do? This equation tells you how changing concentration will change rate, right? Let me ask you some very simple question here first. When we increase the concentration, how will the rate change? Rate will increase, right? Yeah, so this is exactly what we learned in the rate chapter when we learn about collision theory. But this equation shows you how changing concentration will increase the rate. But then you see rate is dependent on three things, not just on the concentration of reactant. What else does rate depend on? Rate also depends on rate constant. Rate also depends on the order. Or if you don't like to call it order now, you can just call it power. Get the power of this term. So therefore, rate equation in a nutshell means rate depends on three factors. The rate constant, the concentration of reactant, and also the power, okay, which we call the order. So can you put down what does the rate equation do? So rate equation shows that rate of reaction is affected by three things. Not just the concentration you learn in the rate chapter. We have one new thing here, rate constant. So this is new, so I'm putting it down here. But concentration is not new to you. You have learned that. So concentration of reactant or reactants. Sometimes there could be more than one reactant. And finally, we have something new again. It's the order of reaction. Okay. Now let me start by introducing you to the order of reaction. We have three different types of order of reaction. It can be zero, so usually zero, primary, or secondary. Okay, zero order, first order, or second order. Okay, so these are called the order of reaction. Let me explain to you what order means on the side, but you have to put down this equation first. Yeah. And if a reaction has more than one reactant,
Sorry, the yellow.
yeah. Let me not use yellow. Okay, from this point on. But it says order of reaction. It is usually zero order, first order, or second order. You will know what these terms mean shortly. What does zero order mean, first order, second order? But put it down first. Okay?
Rating interference of lights.
Sorry.
They also have order.
Yeah, like there is also like a degree sign in here. Okay, so yeah, what about if a reaction has more than one reactant? Okay, let's say A and B. Then the rate equation will become rate equals K A to the power of M, B to the power of N. So if you have two reactants, then there will be two terms, not just one term. Okay, if there are three reactants, then you will add another reactant C here, raised to another power O. Okay, so the takeaway message here is, if you have one reactant, you will see one concentration term. Two reactants, you will see two concentration term. Okay, so write down one reactant means one concentration term. This is why you only see one concentration term here, not two. But then why are you seeing two concentration terms here this time? Because some other reactions may have more than one reactant, right? I mean, more often than not, there are a lot of reactions that have more than one reactant, right? So you have two reactants. Two reactants mean two concentration terms, each raised to their own power. Okay, so each raised to a power of its own. So those power, we call them the order. Yeah, in math you call these the power of a number, but in chemistry we call them the order of reaction. Okay, so I know this is all very confusing, okay, but trust me, on the opposite side I explain to you what zero, first, and second order mean. So what does order mean? Okay, that's maybe the most important question to ask. Yeah, but put this down first. Each raised to a power of its own. You see, A has a power of m. B has a power of n. Yeah, m and n, they can be the same or they may be different. Okay, and we'll know how to find them shortly. But then, on the opposite side, I want you to put down what does order of reaction mean. So what does order of reaction mean? Okay, so starting with zeroth order. So sometimes when you change the concentration of a reactant and you study how rate changes, so there are three possible outcomes in chemistry. So one is that when you change the concentration of reactant, the rate doesn't change at all. We call this particular type of order zeroth order. Sometimes when you raise the concentration of reactant and you see what happens to the rate, it increases linearly. Okay, so this is what linear increase means. It means when you double the concentration of reactant, you get a double in rate. Yeah, what you do to the concentration of reactant, you see the same thing happening to the rate. We call this type of order first order. And then there's a third possibility, which looks like this. Okay, there's an exponential relationship between rate and reactant. So let me turn it into words, okay, so you know what I'm saying here. So these are three different orders. Can you put down zeroth order? So the first one is zeroth order. If you don't feel like writing so many words, you can write 0 degree. We have first order, which is 1 degree. And then we have second order, which is 2 degree. Okay, a reaction, or I should say a reactant, can only be one of these orders. It cannot be zeroth and first at the same time. Okay, so put down this statement on the side. A reactant can only have one of the following. Okay, so can only have one of the following. That means it can either be zero order or first order or second order, but never more than one order at the same time. So what does zeroth order mean? Zeroth order means no matter how you change the concentration of reactant, so no matter how you change the concentration of reactant, does the rate change at all? Look at this graph. When I slide, imagine that I can slide the concentration of reactant to however high or low value I like. You see, no matter what value the concentration of reactant has, the rate stays the same. That means the rate is not dependent on the concentration of reactant. Okay, so this is what zeroth order means. So write down this description on the side. No matter how you change the concentration of reactant, the rate will not change. Okay, so the rate will not change. So for this particular reaction, the rate equation becomes rate equals K, concentration of reactant to the power of 0. And can you tell me what happens when you raise a number to a power of 0 in math? It becomes 1. So that means the whole term is gone, and it will become just K. Okay, so put down something you learned in math. Recall that x to the power of 0 means 1. This is in math. I don't know how to explain this to you, but you know this whole thing will become 1. So 1 times K would just be K, right?
Yeah.
And what do we call K again? Rate constant. So this is why it looks like a dead person, okay? Like with a flat, like a heartbeat or something.
Yeah, heartbeat.
Yeah, okay, so you have rate equals K equals constant. This is why it doesn't go up or down, okay? So you have rate constant here. We'll go first order. First order and second order is something that you may already know. When you change the concentration of reactant, you expect the rate to change. Okay, so this is what we learned in the rate chapter. But as you can see, there are some reactions that are zeroth order. So increasing concentration may not increase the rate of those reactions. Okay, maybe let me give you an example of a zeroth order reaction. So like nitrogen, or I should say ammonia, can be broken down back into nitrogen and hydrogen. in the presence of a catalyst, platinum. Okay, so platinum is a catalyst that provides a catalytic surface. And ammonia, these chemicals, they will attach itself onto the surface of platinum, and then they will be broken down back into nitrogen and hydrogen. So 3 of the hydrogen. So these are hydrogen and this is nitrogen. This is ammonia. So why is this reaction zero order? That's because the catalyst, platinum, okay, it has only a surface, like a certain surface area available. You see, it only has got this much surface area, right? Yeah. Imagine what happens when I put one ammonia here. Well, the ammonia can come in and becomes nitrogen and hydrogen, right? No problem with that, right? But eventually, when the whole surface, you have learned something similar to this in biology. How many of you do biology? Not many, it seems. Okay, well then I cannot use that example here. Okay, later I'll explain this to you. Okay, if you do biology. But imagine what happens when you get the entire platinum covered with ammonia. Can additional ammonia join the surface of the catalyst if it's already fully occupied with ammonia? No. That means increasing the concentration of ammonia. I don't care how many ammonia is waiting on the outside. As long as it is fully occupied, all the sites on platinum, increasing the concentration of ammonia, will it have any effect on the rate? No, because it's already fully occupied. So this is how you understand it, okay? Can you put down this description below? At first, let me not use the color yellow, sorry, okay? So at first, when the surface of PT is not fully occupied, then yeah, you can say increasing concentration of ammonia will increase rate. Because at the beginning, when let's just say there is a 1,000 cm square available on platinum, and then you have only 2 ammonia by the side. Well, yeah, of course, if you have just 1 ammonia, you can only get 1 nitrogen and 3 hydrogen at one time. But if you have 2 ammonia coming, you will have 2 nitrogen and 6 hydrogen, right? So at least at the very beginning, when the surface is not fully occupied, increasing the concentration of ammonia can actually increase rate. But then, let's fast forward, okay, this process here. If you add more and more ammonia, there will be a time when all the platinum surface becomes occupied, right? And by that time, if you increase the concentration of ammonia further, so that there's now more ammonia waiting on the side, do these ammonia get to participate in this reaction when this is fully occupied? No. This is why the rate will remain constant in here, you see. Do you get this? Or no? Okay, in biology, you may have heard of enzymes. Enzymes, when you increase the substrate concentration, the rate will level off, right? Yeah, so this is the same concept. When all the active sites on the enzymes are occupied, increasing substrate, would it result in any further increase in rate? No, right? Yeah, only biology student will be able to relate to what I'm saying now. Okay? Yeah, but it's a similar concept. So you can say, put down this statement. Okay, eventually, when the entire surface of PT is fully occupied, so it's fully occupied, then increasing ammonia concentration further will have no effect on rate. Okay? Is this clear? Yes. Okay, yeah, so this is quite complicated. But don't worry, they won't ask you to explain why some reactions are zero order. We just have to appreciate that, well, yeah, sometimes reactions are zero order. It's a fact. Okay? But this is when it will happen. What about first order? First order and second order, they actually makes a little bit more sense because increasing concentration will increase rate, right? But there are 2 ways the rate can increase. When you double the concentration, so when you double, let me put it when you multiply the concentration of reactant by 2, rate will double. When you triple the concentration of reactant, rate will triple. So basically, whatever you do to the concentration of reactant, the rate will change by the same amount. What kind of relationship are these? This is directly proportional relationship, right? So when you double the concentration of reactant, let's say I drag the value of reactant from this point to this point. So if this means doubling, you see the rate changing by the same amount. So when this x value increases from here to there, the y value will increase by the same amount. Okay? So this is what we mean by first order. Second order is different. When you change reactant, okay, concentration, let's say you double it, you don't just get a doubling of rate, you get a quadrupling of rate. So let me put this in here. First order means when you multiply the concentration of reactant by 2, rates will double, right? What about in second order? It will be 2 to the power of 2, 3 to the power of 2, n to the power of 2.
Oh, yes.
Yeah, so this is, I think, a bit of math involved in here. So for those of you wondering where does the number 2 go? The number 2 goes here. Where does the number 1 go? The number 1 goes here. And you know any number raised to a power of 1 is the same number, right? Yeah, so this is to say, and actually you can do this here. Yeah, when, yes.
Example of first order and second order.
Oh, actually first order and zero order, they can be explained by the same reaction here. At the beginning, remember, when the surface is not fully occupied, increasing the ammonia concentration will actually increase the rate. Right? So you can say at the very beginning, it is first order to ammonia. But then when the surface becomes fully occupied, you see it's very crowded now. No more ammonia can join. At this point, you can say it's zero order. So this is why in biology, you will have seen a graph that looks like this, right? The enzyme, about how enzyme work. When you increase the substrate concentration for a certain time, the rate will actually increase. So that means this is first order in here. You see a graph looking like this, right? But eventually, when you increase the substrate concentration to a certain amount, when all the enzymes active site become saturated, it will become zero order again.
Yeah.
So therefore, they will give you a graph that looks like this and ask you what is the order in this part and in this part of the graph. So we will have to chop this graph into 2 halves. And can you write down in this first half, what order is this?
First order.
First order. So you can see this part in here, exactly, right? And then the second half will be zero order. Okay? So the order can change, okay, in the middle of a reaction, for some reactions. But for most reactions, it will usually not change, okay? So for some it can change, but for some it will not. So you have zero, this is first order. And this part here will be zero order. Okay? So how do we find the order of reaction? Okay, so let me put this on the, I think I have some short exercise here. Okay, if you have the worksheet, you can take it out. If you don't, I will just write it on here. So if the rate equation of a chemical reaction, we are on page 2 by the way, we are on page 2. If the rate equation is shown below, how many reactants are there first in this reaction? There are 2 reactants. But what is the order with respect to? Okay, we say with respect to because each of the reactants will have a power. What is the power you see for Cl2?
Zero.
If it is 0, you will not see it. It is actually 1. Okay, so can you put down Cl2, the order is 1. For NO, the order is 2. Yeah, don't say 0. Because if it was 0, the whole term would disappear. Okay? Yeah. The first question. So what do we mean by overall order? Overall order means the sum of index.
Oh, okay.
Yeah, so you have 1 and 2. So what is the index sum? 3. Yes. Okay, let me give you another sample equation here. You see the actual questions are actually quite simple. Don't worry. I don't want to scare you, okay, but the actual question is actually quite simple. Can you write down, if you have got the worksheet, what the overall order is? Overall order is actually the sum of the power combined. Of course, if you have more terms, if you have more reactants, of course it will be, a bigger number, okay? So overall order is sometimes larger than 2, but the individual order can only be 0 or 1 or 2, okay? So you can write that M or N is usually 0 or 1 or 2, okay, M and N. Okay, and that's it. We are already done with one question. What about question 2? So the order with respect to F2 is 1, and the overall order of the reaction is 2. So what is the order with respect to NO2 then? 1, yes, okay. And from this example, I wanted to learn another thing. Is that does the order have anything to do with the mole ratio? No. If you see that it is equal to mole ratio, it's just a coincidence, okay? Can you put this very, very important point down? Maybe red, please, okay? So the order has nothing to do with the mole ratio. Don't think, oh, because I see X, I see Y in here. The mole ratio is the same as order. No, it has nothing to do with the mole ratio, okay? So it has nothing to do with the mole ratio. This is why when you read the notes, maybe you're kind of confused. Why did I put X and Y here when X and Y don't even appear here? That's because they are not related. Okay, so this is why you don't see X and Y at all in the rate equation, as it has nothing to do with the mole ratio. Okay? Right. So, very important. Next. So, can you write down this equation properly? So if the order of NO2 must be 1, because the order of F2 is 1 and then the overall order is 2, 2 minus 1 would just be 1. So the order is 1. Can you write me the rate equation? What is the first term that appears in the rate equation? K, small k, remember small k. I know when you write k, a lot of students would just write small k like this and big K like this, and if you ask me, I have trouble telling them apart, which is why I write k this way, the small k.
More beautiful.
Yeah, if you say so. But just know, okay, that there is Kc, and then there is small k. You can of course write small k like this. If you know how to tell apart the big K and small k, you can do this. But I would recommend you write like this, okay, the small k. So and then what?
NO2.
NO2. What is the order? 1. And then what is the other?
F2.
F2. What is the order?
1.
So this explains why the overall order is 2. So you see, when you apply it, it's actually quite simple. Okay. Now let's try question 3. The rate equation is like blah blah blah. Okay. So what is the unit of rate constant? Okay. So now I want to draw your attention back to the equilibrium constant and the rate constant. So equilibrium constant, Kc, versus rate constant, K, small k. So both of them can have a different unit, right? Do you remember?
Yeah.
Yeah, so both, they have some similarity. Both may have different units. Not like concentration. Concentration must always have the unit over the cube, okay? But Kc and K, depending on how you write the equilibrium, it is different. Okay, so let's take a look at the units of Kc first. Okay, recap. Imagine that I have this equilibrium. 2A becomes B, and then I have A becoming A plus B becoming C plus 4D. Can you write me the equilibrium expression? Maybe I'll do the first one for you, just to refresh your memory. Kc is written with product on top and reactant at the bottom, and they are raised to a power of their mole ratio. So you have 1 and 2. Let me finish this first. And so how many concentration terms are there on top and below? 1 and 2. So you can do mole per dm cube on top, and then you can do mole per dm cube raised to a power of 2 at the bottom. So what is the units then?
dm³ per mole.
dm³ per mole. Or you can first write mole per dm³ to the power of -1, and then you can expand it and write dm³ per mole. Right?
Yeah.
Remember this? Yeah, so this is why I said the units of Kc depends. So with K is similar. Now I want you to do that as homework. So unit of K. If you have rate equals Ka compared to rate equals Ka squared. How do you write K? K, by rearranging subjects, you will have K equals rate over A, right? Yeah, what's the unit of rate? Rate is mole per dm cube per second. Concentration has the unit mole per dm cube. So when you stuff this back in, and when you stuff this back in, what will you have as the unit? When you divide mole per dm cube per second by mole per dm cube, what do you get? Just per second. So now I want you to just try that question, because depending on how you write the rate equation, the unit of K would differ. Okay, so you can work out the answer to this question. Yeah, there are two reactions here, meaning there are two concentration terms. So each concentration term has mole per dm cube as unit. So when you divide rate by that, figure out the unit of rate constant. Okay, so we'll